So in this video, we are going to look at three different neural network architectures, namely multi-layer perceptron, convolutional neural network, and Y-shaped convolutional neural network to solve the problem of recognizing a digit, handwritten digit in an image. So all of these images are available in a dataset known as MNIST, and to implement these three architectures, we are going to use Keras API. So the objective is mostly to do the coding part and for these three different architectures, and we can use some of these learnings in a more complicated architectures in a later videos. So in order to set up the TensorFlow, after setting up, I use this code to recognize whether or not my code is using GPU. So in particular, these two lines help us to know whether we are using GPU or not. Although my laptop has a GPU, the packages are not set up to utilize the GPU, and you can check it by using this code specified here. So most of these computations are going to be done within CPU, and it's more than adequate for these examples that we have today. So the setup that I have is I have a project folder NN Keras, I have a data folder, notebooks folder, and images folders. So let's look at the data itself, the MNIST image data. So you can load that particular data using this MNIST.load data, which is available in this package MNIST. And once you load the data, you will get these two pairs of tuples. One is for training and one is for testing. So when I look at the shape of this training dataset, you have 60,000 28 by 28. Each of these 28 by 28 is a NumPy array with values within it, right? So these are the values that you can see. But let's look at what the shape of the image is 28 by 28. And if you look at what it has, I try to display in pandas data frame, and you can see a 28 columns and 28 rows, and the higher the value, the brighter it is. So it's the whiter is 20 to 55, and the 0 is dark color, and anything in between is the gray color between that you see in an image. So to be exact, the image looks something like this. So this is a handwritten image, and we are trying to recognize it, right? So to look at a few more images, this is the Python code, and you can see the images within MNIST data are shown here. So let's look at how do we write the code of multi-layer perceptron. Essentially, in a multi-layer perceptron, you have an input layer which takes in the raw pixel values. So in this case, we have 28 by 28, so there are 784 image values. So we will have x1 to x784. Those are going to go in the input layer. Then we have a hidden layer, then have a second hidden layer, and then finally we have another dense layer with the activation function as softmax, which will provide us probabilities of which class it belongs to. The only difference is that we have 10 output classes, so we will see 10 classes here, and the input layer will be 785. So let's we looked at the data and how it is. Now let's process to run through a multi-layer perceptron. So the first thing I did here is to try to change Y training data, which is essentially a single digit representing what digit it is, to a class data, or essentially what I did is a one-hot encoding. So it's a vector of 10 digits representing a value of 1 representing what digit it is. And then I have the input image, as you can see, is 28 by 28, and that one is converted into 784 by multiplying, and I'm using the function called reshape to transform it into 784. So that is what we are going to feed here. So I'm converting into 784, and also converting the values 0 to 255 into a decimal value 0 to 1, which ranges in 0 to 1. So it's easier for neural network to process the values that are between 0 to 1 rather than these um, a numerical value from 1 to 20 to 55. So before processing, we had our data set as 6,000 images with 28 by 28. Now we have 6,000 images with 784 single dimensional data. So we are going to use Keras. Keras essentially has like 4 or 5 steps. The first one is define the architecture. So the definition of architecture is done here. We are saying the model is going to be sequential, and we are going to say the first one is a dense model with 256 hidden units, which is defined here. And then the second is also a dense layer with 256 units, and the third layer is a dense layer with 10 units with activation function as softmax. For the other ones, we are doing a nonlinear transformation using activation function ReLU. As if the input dimension is 784, we have to specify the input dimension for the first layer. Right. And then once we define this neighbor, we can display or we can summarize the model. I will show the plot here, which is given here. So the plot function essentially tells us what we built. We built a something that takes in input as 784. We are feeding that into a dense layer of 256, and then those outputs are fed into 256, and then those again fed into dense layer of 10 network, which will produce the output as what we need is probabilities of belonging to each class. So that's what the plot image will do. And then we have another a function called as model.compile. So this is where the model will learn the weights. This is how it will learn. So we are specifying use the loss function as categorical cross entropy. So we have 10 classes. So this is the ideal loss function to use. And then we are using optimizers atoms. There are others available like SGD, RMS prob, and adaptive momentum, and so on. So we are using optimizer as atom. You can explore other ones, but this is adequate. And the metrics that we are displaying is accuracy. So again, we are using the model.fit, so where we are giving our training data set, which we modified, and then the Y train, which is the one hot encoded one, and we are saying number of epochs as 3. So this 3 indicates that we are passing our 60,000 images, all of those images 3 times into the network. And the batch size, we are specifying these are the number of records that are given to the image at once, and we have to update the weights at each of those batch size. So that's exactly what's being specified here. The history will store the values of accuracy that it obtains over the period of time when we are running this epoch. And once we run it, it has learned the weights. We can then save it to an image, and then we can load that image back again when we want to run to do our predictions. So the predictions, you can run it as model.evaluate, and we can give X test and Y test and the batch size. So the predictions can be stored here. So let's look at closer look at the predictions. So when you print the predictions, what you see is a probabilities with the probability highest probability at index 2, which indicates that we have 2 as our digit, and the same thing Y test, which is the input data that we gave it to the neural network, which has a 1 at index 2. Right. So let's improve the code a little bit. So there are 2 things that we can do. Instead of doing the reshaping, so remember I loaded the data again, which means it's in the raw shape, which is 28 by 28 is our input shape. So rather than modifying externally, we can include a flattened layer. What it does is it takes a 28 by 28 and makes a flattened layer of 784, and then you can also do the scaling within the layer itself rather than doing it externally. Again, the dense layer, which is very much similar to what we have done before. We are introducing regulatory layers drop out. So except for these three, the flatten, rescale, and drop, everything is more or less the same. You can see the structure here, the sequential. Within that, I specified an array, and each of the element is a layer that we have specified here. It's a convenient way of specifying a sequential model. Once we have the model, we pretty much do the same thing as we have done before. So model.compile, history. In this, we introduce one more thing called validation split, so that when we are running our epochs, we can see how much accuracy we are getting at each stage. In terms of saving, and we can save weights as well. Once everything is done, we can save the weights at this checkpoint, so that we can load it at a later time to run evaluation or to do predictions. So evaluation is done as similar to what we have seen before, and the model can be printed similarly, right? So one thing we did not do is, when we say model.summary, this is what it does. It shows a number of parameters. So the number of parameters is essentially the input times the number of layers that we have, plus the number of biases, which is equal to the number of hidden units that we have. So if you multiply 784 by 256 and then add 256, you're going to get this as parameters. So far this is very much straightforward. So you can see the accuracy is being printed because we provided a validation dataset as well. As you can see, the accuracy on the test dataset is 98, which is pretty decent for this dataset. Right? So if you want to look at the layers and the weights that we are learning at each stage, right? So you can print it out. For each layer, print layer.get weights. So for flatten, we don't have any weights. For rescaling, we don't have any weights. For the dense network, we do have weights, and the weights for biases and for weights that are coming from each input for each unit are presented here, right? Also, from history has these four keys: loss, accuracy, and validation loss and validation accuracy. You can take these key values and plot loss as well as validation loss. That shows us how our validation dataset is using compared to the training. As you can see, the training dataset, the validation is improving, but it kind of stabilized after 12 or 13 iterations. So you can improve the model by specifying all of the parameters in a function, and you can call that function by giving the input shape, and rest of the code is more or less the same, but this improves the readability of the code. All of the definitions of the neural network is specified here, and rest of the whether it's a model, fit, or evaluate is being called as usual. So as you can see, the test accuracy is about 98.1. So if you are given image and if you want to run some multi-layer perceptron, there are additional steps that you can employ. You can do feature modify the data and generate additional data. For example, you can change the pixels, you can magnify the pixel values, or you can move the images to the left or to the right, or rotate it and so on, and generate additional data sets. You can also save these weights learned at each stage as their model checkpoints, and you can use right set of parameters. For example, I use number of hidden units at 256. How do you learn those? You can iterate through, like, experimenting, like 64, 32, 256, 128, and so on, and check which ones actually give you the better number of hidden, number of layers as well. I use 2 here. I use 3. You can use 4, 5. You can iterate through and learn which one gives better results. So now we are going to look at convolutional neural network, and so for images, convolutional neural network is considered to be the best way of working with it, because it if you look at an image, the meaningful parts of the image are more or less localized. What happens in one corner doesn't really impact in the other corner. Whereas in multi-layer network, we are using every pixel and connecting to every pixel in the network. So there are only sparse interactions, and if we can encapsulate those interactions, we can uh, learn efficiently. So convolutional neural network, they can generate, like if there are, let's say, edges along the images and various sites, we can detect those edges. If there are loops, we can detect the loops in earlier stages, and we can combine what is learned in the first stage and aggregate them in the later stages, and we can learn what is happening in the level the way human recognizes certain things. Like for example, if I look at an eye, if I look at the hand, I can if I look at the shape of the body, I can detect who that person could be. So you're not detecting the like at the pixel level, but more at the aggregated shapes, and that is exactly what is being done in the convolution, and it does efficiently through operations like pooling and so on. So for the implementation, what you can see here is you have convolution here, you are doing max pooling, again convolution, max pooling, you can repeatedly do that. Finally, after learning the features, we are then flattening whatever we learned, and then we are doing whatever we did before, which is creating a dense layer, learning a network, and again a dense layer, learning a network, and then finally outputting to a softmax layer. So all of these steps before this flattening is learning features the way human eye learns to some extent, and it learns it efficiently. So you can consider this as learning features stage, and this one is learning weights to generate the required outputs. So again, if you look at I think I did not input this one, so let me try. Yeah, it's trying to load this data, but I already have it. But so you can see that the input for convolutional image is 28 by 28 by 1. This one, if you have a color image, you will have RGB, so this will be 3. So the convolutional neural network expects a number of channels here as the input. So you will see, that's why I'm using this reshape input shape. It is, which is 28 by 28. I'm adding 1 to it. I'm saying that there is a additional channel which is 1. If I'm using a colored image, I will have RGB, then it will be 3, and so on. Then I'm applying a convolution with a number of filters 6, and kernel size as 3, and padding same. You can use different kinds of padding. You can specify kernels as 3 by 3, or you just simply specify 3. Again, pooling can also be specified as just 2 or 2 by 2. Just so if you're I have one particular note from one of these websites where they specified how to look at a convolution. So essentially, if you're thinking of a convolution, you have an input image and you're multiplying this filter. This is a filter which will generate a feature map, and the output is shown here. Essentially, you're multiplying each of these cell value with the other cell value, and you're adding them up, and you can generate this value. You repeatedly do this until you generate the outputs. So this is fairly straightforward, but the important thing is, like when you have RGB image, you have 3 channels or 3 filters RGB, and the filter should match this number of channels. So you have 3 images, but the output of this multiplication is again a single dimension value as shown here, right? So if you are using 2 filters, you are generating through 2 channels. So that is important to understand here. And convolutional involves not only applying filters, but also going through the process of activation of ReLU. That's what we are specifying here activation as ReLU. So there is also pooling layer which will reduce the sparsity of it, and then finally you just apply flatten, and then on top of it then you can apply hidden layer like a multi-layer perceptron that we have done before. So the other steps, model.compile, model.fit, and evaluate are very similar to what we have used before. So you can see once we apply convolutional neural network, the prediction accuracy improved tremendously, 99.3%. So the important thing to remember when you are running these is to understand the input shape that goes into it. And again, I'm using reshape and rescale rather than use changing them on the NumPy array. I'm using the layers to do the processing. So one of the things that happens in neural networks is that not all the models are linear. So I'm going to look at a Y-shaped CNN, which is something like this that is shown here, multiple inputs and the same output. So for these kind of networks, the sequential model no longer works. So sequential model is essentially we are adding one layer of the other, whereas in functional API we are specifying in a different way, where we are specifying inputs as well as outputs. Once we have this, we are much more flexible to give complex graph topologies using this functional API. So let's look at that example of functional API. So you are specifying the inputs. Again, for that we are specifying the input shape, and whatever the input is going as a output input for the next layer, and we are doing a reshape operation, and the output coming from this reshape operation is being fed as input to the next layer, and so on. What is important for a functional API is the inputs and outputs. So we essentially coded the sequential coding that we did before in a functional API form. Here everything is same. You're doing a compilation, you're doing the summary. One thing that changes here, when you're building a model, here you are calling model, and then we are specifying inputs, the format of the inputs, and the outputs, and the format of the outputs. So this is the difference between sequential model and here. When you're using sequential, you say model is equal to sequential and that's it. Here you're specifying model is equal to model and specifying what are the inputs and what are the outputs. The inputs and outputs I define here, and I'm specifying those in these arguments. So once you have the model fitting part, the evaluation part is the same. So and then finally even to plot, it's the same thing. So you can see the output of this functional API is very similar to what we have done before. So let's look at Y-shaped convolutional neural network. So the reason for looking at Y-shaped convolutional neural network is when we are implementing complex topologies, this particular coding will help us understand how that topology is being built. So in this case, I am passing through two convolutional neural network. One input goes through this path and the other goes to this path, and then we are combining the outputs from the flatten, and then we are going through a multi-layer perceptron process, and then finally generating our outputs. So this is the code that I gave to generate the inputs for the left side, convolutional, and the right side. Again, this is a functional API. So we have inputs and outputs. So I'm returning inputs and outputs from this definition and inputs and output from this definition. So they can be identical, but here I changed a few things from the left side processing and the right side processing. So one of the things that you see is the dilation rate as to and the again dilation rate is 2, whereas here the dilation rate is 1. So to understand the dilation rate, you can see when we don't specify any dilation rate, the convolution is being done by we are multiplying in this way, whereas when the dilation is 2, we are skipping certain. When retina is dilated, it actually enlarges, so you are seeing a far apart pixels. So in this case you are skipping certain pixels in between, and you are multiplying your convolution filter with these pixels rather than these consecutive pixels. So when the dilation is 3, it is skipping 2 images and using these pixels to multiply with the filter. So that is what is being done in these calls. The dilation rate has been increased. So although the it looks a convolution layer, the images are going through different processes, so they are learning different features. So once the features are being developed, they are being concatenated. So you can see here here we are concatenating output 1 and output 2, and then this becomes the input for the next layer, for the dense layer, and then we are dropping it out, and we are giving this output as input for the next layer, and finally we are giving this input to a soft mask layer to produce our results, right? So we have defined what the output layer is, and we have defined what are the inputs should look like. So you can see the inputs are for this left CNN is this input object, and for the right one is this input object. So you have to specify those in the model definition in the functional API. So the inputs are given in the form of an array. So input 1 and inputs 2, and the output layer is essentially this output layer. This is how you build the model, and you can compile the model by giving the loss optimizer and so on. One thing that is different from the previous one is you're specifying xtrain and xtrain as input, like an array, because the model that we have defined it's an array of 2 inputs, so we have to give 2 inputs, and the output is one hot encoded output, so which is the same thing that we have seen. So this is one output is good enough. This particular the way of giving inputs should be consistently given in evaluation as well as prediction. So you can see the prediction also requires 2 inputs, and the evaluation also requires 2 inputs. If you are doing this kind of complex networks for the first time, some of the confusion occurs here. So as you can see, the image what we have done, the model it is going through different transformations. Here I have one more convolution layer compared to here. So we are getting different outputs from the left side convolutional layer. Here we are getting a flattened layer of 128, here the flattened layer of 1600. We are merging them together using the concatenate, and then that is generating 1728, and that we are feeding into 256, and then again 256 dense layer, and finally we are getting an output of 10. So if you look at the results of it, you can see it is generating an accuracy of 99.2%, but I ran it, so it's definitely better than Multilayer Perceptron, but it's slightly lower than a simple convolutional neural network, because this is a simple problem, so we don't really need to do this complicated architecture, but I did it so that we understand how the somewhat complicated architecture can be developed. So to recap, so in this particular notebook we learned how, let me see, yeah, how we can code a multi-layer perceptron, how do we look at a convolutional neural network, and Y-shaped CNN to solve the problem of recognizing a handwritten digit which is stored in the form of an image. So I hope the coding part of it there are many tutorials available outside, but the coding here can help clarify certain things, and definitely will be useful for future uh, problems that we are going to solve.